Okay. Nick's here. Sagan. Clay's excuse today. Rachel. Kendrick. Ethan. Karina. Hunter. Zach. Ty. Brianna. Mayo. McCune. Laurel. Mendez. Miloy. Nick's here. Avery. Aiden. Aiden Roth. No. Nash. Also known as T-Bone. T-Bone's not here today. Will Smith. Sproul. Stahlman, Colton. Tyler. Tucci. And Cuddy. All right. Today we're gonna hopefully finish that in time. Figure out how to. Oops, wrong class. Write code for valuation of an American option on a stock that doesn't pay any dividend. Just a little bit of math. I promise I'm not gonna require any of this from you. Um, we assume a process for the stock as geometric Brownian motion or geometric random walk with a mean growth rate of mu. In fact, we're going to use short-term interest rate for that. Come on. This DZ is known as the Brownian increment. It's a normal random variable that has expectation of 0 and variance of dt, variance of dz is just dt. Okay. All we're saying that stock prices follow a random walk around the trend, where the mean growth rate is the interest rate. And it doesn't matter what that rate is. It works fine with the Black-Scholes taking that as the interest rate. Now we're going to use a transformation of the stock price. This is a weird transformation, but log of the stock price minus r minus 1/2 sigma square t, the whole thing divided by sigma. And there's a reason we're doing that. If you work out the math, you can show that dy is simply equal to dz, which sigma or mu r doesn't appear in that, which means first we're going to construct the tree for y, then we're going to go back to the stock price. You can show that S is equal to sigma times y plus 1/2 plus r minus 1/2 sigma squared. Let's call that x. That means e raised to that power. So if I construct a tree for y, getting the price tree is not going to be a problem. And if you're interested in how I'm finding that, this is used a lot in stochastic calculus. It's called Ito's lemma. Uh, since this is based on a random walk, a different way of differentiation, if y equals a function of s and time, in this case it is, you can write dy as those weird uh, reverse these, they mean partial differentiation, but you don't need to know anything about that. Now, the way we construct the tree, this is 0, this is cap t, where t is when the option expires, or how long we have in terms of years until the option expires. We're going to divide this into a number of steps. I'm just going to do it into 4 for now, just for illustration purposes. We're doing a tree for y now. It could take an up step, take a down step. We're going to figure out what the size of that step is going to be, but for now, next time, or we're going to divide that time period into such small increments. Every time the stock price can either, or this y can either stay constant, it could go up by one step or down by one step. That's it. No other possible values. So next time it could go up, stay same, up, down one, up one, stay same, down one. You know, at time 0, there is only one node. At time 1, there's going to be 3, then 5, 7, so on and so forth. In fact, we're going to name these. So this is 0, minus 1, 1, minus 2, minus 1, 0, 1, 2, so on and so forth. All right? So the first thing we're going to do is build a tree. And on that tree, I need step sizes. And so let's call uh, time step, let's call that dt. That's t over n if I divide it into n steps. So in this case, 4, that would be t over 4. Okay. And little dy, don't ask me why. This is going to be 3 times square root of dt, or square root of 3 times dt. Again, if this was a master's class, I would have gone through the logic behind that. We're basically matching the moments of the distribution, statistical distribution, but you don't need to know that. And probability of moving up is equal to probability of moving down, and they are both equal to 1/6. We did that transformation so that we can have that number constant, and probability of staying same is 2/3. So we're basically saying that at every time step, with a probability of 2/3, y is going to stay the same, and with a probability of 1/6, it's going to go either up or down. Okay. Once we have the y tree, we will construct S3 using transformation above. Now, here's what's important on that S3. I have a generic S3. Okay. Come on. I'm going to have this thing only have 2 steps just for the hell of it.